Hello there. Lecture 9, LU decomposition. Now let's give you guys a brief background, then I will go into the details. In lecture 8, Gaussian elimination, we solved a system AX is equal to B. What we did some row operations to turn AX is equal to B into a new form where an upper triangular A, let me call this A tilde times X is equal to, obviously this is going to be new piece, the B values will change every time we do a row operation. So after that, we will just find xm first, xm minus 1 next, xm minus 2 next, and up until x1. So we will find the values of x backwards. So that's why it is called back substitution. Now, the difference is we still want to solve ax is equal to b, but a does not change. Ax, but we get a new b. So what if I get a new b, another b, another b? Then every time x is going to be x1, x2, x3. These are all vectors, obviously. So whenever we get a new b, again we have to solve this. So if it is we had to do Gaussian elimination, so we have a new system ax is equal to b1, and it is solved. I got another new system ax is equal to b2, where a remains the same, whereas b changes. So that is the problem that, so obviously we want to solve, we can do Gaussian elimination, of course we can, but that will be more costly. So we want to do it efficiently. So how to do it efficiently? We are going to decompose A into L times U. L is a lower triangular matrix, U is an upper triangular matrix, times X is equal to B. So regardless of what B is, we will see if we can do it efficiently. We had to do some Gaussian, we will do Gaussian elimination only once with A, and then we will, any new B comes, we can solve it for X. We will see how. So let's go to the details. Here's the details one more time. So we have Ax is equal to B, that is the original equation we wanted to solve. We turn that into L times Ux is equal to B. So then U times X, we will call it D. So we will solve L times D for times is equal to B. So L times D is equal to B. L is known, D is known, so we will solve for D. And then we will go to the other equation, U times X is equal to D. This is known, D is known because we just solved it. U is known, we will solve for X. So every time there is a new B, we can solve it without doing any more Gaussian elimination. So because Gaussian elimination is a computationally expensive procedure. Now, the remaining question is how to do LU decomposition. Let's get into the details. Here, up to this point, it is explained, but you don't need to go into the details. I can do an example, probably that's the best way. Anyway, let me summarize it, how it is done. We do the fourth elimination like how we do Gaussian elimination, and then we will save those coefficients, and then we will use those coefficients that came in Gaussian elimination. Those are the coefficients that were used to make the L's. So that's a neat approach, that's why we are studying it. So let's do an example. I'm going to explain LU decomposition using this example here. A times X is equal to B. So this is a step. We will do the steps involved in Gaussian elimination, where we will make A into an upper triangular matrix, and the coefficients will be used to form the lower triangular matrix. So the first step is R2 is equal to R2 minus 0.1 over 3. Where did 0.1 and 3 come from? These two. Let me use a different color. 0.1 is here, 0.3 is here. No, the details are in the previous lecture. So R2 is R2 minus 0.1 over 3. 0.1 over 3 is approximated. This approximation is going to cost us no, when you have that kind of rational number, that's where this example serves in another way that it shows that what is the cost of this approximation. Anyway, so that's a coefficient that will be used. We will start with the identity matrix for L, and then that coefficient comes here. So we did our first step in making A an upper triangular matrix. Now we will start with U, and then we will do the second row operation. So those who are wondering where 0.3 and 3 come from, 0.3 and 3 come from here, 0.3 and 3. So that is a second row operation. R3 is equal to R3 minus 0.1 R1, 0.3 over 3 is 0.1. So that 0.1 is used to make the second element there. Third row operation, R3 is equal to R3 minus minus 0.19 over 7.0033. Those numbers come from here. So from that, we get the next coefficient. So that is used to form L3. Now that comes here. So now we have both L and U. So L times U is equal to A. You can check it. If you multiply L times U, you will see that you don't get A. You will get slightly something that is very close to, probably not even very close, closer to A. Why? Because of the approximation that we did. So I agree that probably this is not a good example to introduce LU decomposition, because you will see that, well, LU is not equal to A. The reason I want to tell you up front is that these numbers, the approximation that we did, that is what costed us. Anyway, I'm going to ignore that because the purpose here is to introduce how to do LU decomposition. Maybe next time I will find a better example. Probably this example is from the book anyway. I just noticed this. Okay, so now we have LU decomposition performed. That means we have L and U. So let's go here. So what we do first, we find D, that L times D is equal to B. B is already known. L we just found. So what is D? So for this we can just use therefore can use solve the, no, that is wrong. Forward substitution. I will change it in the lecture on forward substitution. Therefore can be solved through forward substitution. That is, D1 is straight up, straightly it is 7.85. When you go to the second equation to solve D2, and go to the third equation to solve D3. So we will use forward substitution to find D1, D2, and D3. So now we know D1, D2, and D3. As the lecture says, the next step is solve for x using ux is equal to D. So that is U, the view that we just found here. U times x is equal to D, the D that we just found out. D1, D2, and D3. You will see D1, D2, D3, D1, D2, and D3. So now we will use I wrote it wrong. That will be, we will use back substitution, right, to solve back substitution to solve for x1, x2, and x3. So that is how we use LU decomposition to solve a linear system of equation. The most important thing I want you to notice here is how we got L and U. There will be many other examples. There's homework and there are examples in the book. You can test it, but my goal here in this example is to show you how to obtain L and U, and then how to use that into to solve for X using this approach. Here's another example, example 2, that's here. This is a 4 by 4 matrix, so that is A times X is equal to B. I did not do the LU decomposition in the lecture notes, but I'm assuming you can do. The good thing is about this example is you should try, because there are no fractional numbers and there are no errors, approximation errors. So it would be nice if you can do that. But after you do this, you will get L. You will get the following. This is also a good way for you to check and see if it works. That will be L. That the L you will get, and that is a U. So once you have L and U, we want to solve it for L times D is equal to whatever the B that was given. This is B. So through that, again, that is not back. We will do this to forward, because we will get D1 first, D2 second, D3, D4, right? So that's forward substitution, and you will get this for D, and then you will solve for U times X is equal to D. That is D. So now we will use back substitution to get for X. So that's an example that you should try. If you can do this example, get the same results, and you understood LU decomposition. Now here is another question, just to elaborate more on LU decomposition. Solve the following linear system of equation through LU decomposition. You will see the A is the same. A is the same as before. What changed is B. Only B changed. It's a different number, 2, 7, 7, and 15. So we don't need to do LU decomposition again, because it is only done on A. So L and U are going to be the same. So we will just solve L times D is equal to new B. So we will get a new D. Then you solve U times X is equal to D, and then you will get X. That's it. So through example 2 and 3, what we found was, whenever there is a new B vector, so we had to do LU decomposition only one. For the second example here, we did not do LU decomposition because L and U are already known. So we only need to do back substitution, which is much more efficient than doing a Gaussian elimination again. So that's the whole point, and that's exactly why LU decomposition is useful. Whenever a new B comes, and we can solve for it if we can store the values of LU and D, L and U that we got before. Example 4 has a case where when you keep on doing the LU decomposition, you will be stuck where there is a 0 in the pivot position. So for this, you had to do the pivoting approach. You can just interchange those two rows to do that. I again suggest to try that. That the pivoting comes was taught in the previous lecture. Okay, so that's pretty much it for LU decomposition. There's a naive, and so this is the naive algorithm. That is, it does not take into consideration for the pivoting and scaling. I would suggest check the book for a better algorithm. I need to improve this algorithm to improve pivoting and include pivoting and scaling. That way it will be better. So that's an algorithm. I'm not sure if this will be in the labs, but at least I want to get the point across that whatever we study is taught in this class. Whatever is being taught is taught with the understanding that it will be programmed. I want you to realize that we are studying programming. I'm giving you more and more engineering problems to program. Whenever you studied programming before, where in high school or wherever, you did not think of solving this kind of engineering problem in programming. So that's the whole point here. Every engineering problem that is taught here can be programmed. So that's why I'm just throwing in that algorithm there so you can think about programming. All of these won't be done in the lab. You should try programming yourself. For example, you can write a program to solve all this homework. All these won't be assigned. All of these won't be assigned as homework. But obviously, you can write a program for LED decomposition. Then you have answers for all the questions. You just punch in the values, you get the answers. Very easy to do your homework, and you will be sure that the answers are correct rather than doing it by hand. Okay, so that's it. Now I'm going to start another topic: how to use LED decomposition to find matrix inverse. Matrix inversion. So we have a matrix A. We want to find A inverse. So we know that A times A inverse is I. I is a diagonal matrix. That is 1, 1, 1, 1, like that. Everything else is 0 iota. Looks like iota. Yeah. So that's a 4. That is an I4. So how to find a matrix inverse? So we will solve for AX1. So the goal is to find A inverse. We will solve for this X1, this X2, and this X3, and A inverse is basically X1, X2, X3. That's it. So how to solve for A in X1, X2, and X3? We can use LED decomposition. And then what is I1 and I2 and I3? These are very special matrices. That is each row of the identity matrix. I1 is 1, 0, 0. Obviously, it's a 3 by 3 example. I2 is 0, 1, 0. And I3 is 0, 0, 1. So I1, I2, I3. So if A is 3 by 3 in this example, so A is 3 by 3. So A is 3 by 3. So AX1 is equal to I1. You solve it, you got X1. AX2 is equal to I2. Solve it, get it for X2. AX3 is equal to I3. Get the values for X3. And A inverse is X1, which is a 3 by 1 vector. X2, which is another 3 by 1 vector. And X3, another 3 by 1 vector. That is A inverse. So that is what we are going to do. Let's start. A is here, sorry, A is here, and then I skip the steps for LU decomposition, but you can do LU decomposition on A, and you can check. It's a good way to do it by yourself and check the values. So you will get the values shown here, U and L. That's what you will get for. So this is the same, also the same example that we done before. And you will notice one thing that these approximations sometimes that we did here because I created this in a computer, sometimes you might see some discrepancies, but you can always ask me for explanation why if you don't get exact values because let me elaborate that. For example, even though it is 0.00033, it is actually 0.03333, like that, right? So I might have used a bigger steps in the computer, so that way you didn't get that results. Okay. So first we are going to solve A x1 is equal to I1. So we have three problems here. we have three problems here. That is, problem 1 is this, problem 2 is 3, problem 3 is here. AX1 is I1, AX2 is I2, AX3 is I3. And we already decomposed A into L and U. So we have just used the forward and backward substitution to find x1, x2, and x3. So for the first problem, we take I1 and then first find D1 and then find x. So that is the first x. Second problem, find x2. So we will use I2 and then find D and then x. That's the second problem. Third problem, you find x3 here. So A inverse is x1, x2, and x3. So that is A inverse. So if don't use a calculator, if you can do this in a computer like MATLAB or anything, or even if you're using a calculator, use as many digits as possible. Like here, don't truncate, don't make truncation errors. Again, I agree, this is not a good example where the good example, the one where there's no fractional numbers. So anyway, I am sure you can understand that. So that is your A inverse. That is your A inverse that you got. Now, what you can do is go and check what is A times A inverse. You know that it should be I 1 0 0 0 1 0 0 0 1. What is A inverse times A? It should also be the same. It should be an identity matrix. So that's how you can check. You can take another example and maybe take another example from the book where I would probably change this for the next time, where there's no fractional numbers and this approximation. There is a little bit of distraction, but probably one of the homeworks is not like that. Or you can find the inverse of this matrix. This seems to be so yeah, I would suggest you try this for finding the inverse. So A is here, so that is A. Let me write this a little. You can find the inverse of this A. Find A inverse. So that's going to be, so you had to solve four problems. So you had to solve for A x1 is equal to 1 0 0 0. And then A x2 is equal to 0 1 0 0, and then A x3 is equal to 0 0 1 0, and then A x4 is equal to 0 0 0 1. So A inverse will be x1, x2, x3, and x4. Then you can, that's, so you already have L and U, so it should be very fast to check that, and then you can check what is A times A inverse times A. The good thing about this example is that there are no fractional numbers, so you don't need to worry about how many digits to keep and all that. Once again, I would suggest doing this using a program. Write a program to do this LED conversion, and if you make the program general enough so that don't fix it as a 4x4 or 3x3, make it as n, write it for n by n, and that will be, then you can check all of these examples using that. That's what I do actually in MATLAB to create this. But if you're not familiar with MATLAB, you can write the program in C++. I'm not sure this will be in the lab, but definitely this or the Gaussian elimination will be in the lab for you to play with in programming. Let's switch gears. Now we are going to talk about an approach for solving, an approximate method to solving linear system of equations. So we are done talking about these two approaches, matrix-based approaches, Gaussian elimination and LED decomposition. Sometimes if the problem is too big, we want to solve for approximately, how to get approximate solution. So that's the Jacobi iteration is about. So here is an example. So that is in a form linear equations, three equations, three unknowns. So we will use a fixed Jacobi iteration is very similar to fixed point iteration. So first you, from the first equation 61, you get x1. So x1 will be 7 plus x2 minus x3 over 4. And then you get x2 from the second equation 62. That will be 21 plus 4x1 plus x3 divided by 8. And then from the third equation you get x3, which will be 15 plus 2x1 minus x2 divided by 5. So we have three iterations, and then we had to start with an initial guess and then keep on iterating. So that is what is shown here. We start with the initial guess. So you will see that if the initial guess is good, it will converge. Otherwise, it might not even converge. So for the results for 4 steps are shown here, and that's just an intuitive and iterative approach. So an example is given here for the same example. No, it's another example is given here. So I have given two examples for Jacobi iteration, and then there's another iteration called Gauss-Seidel iteration. Let's so here, I mean, it is very similar to x1, x2. I mean, similar to the Jacobi iteration. The only change is that we use the latest values for the x1, x3. Whenever you go to the next iteration, let me explain that a little bit further. The difference between Jacobi and Gauss-Seidel iteration is that in Jacobi we start with three initial guesses and wait until new x1, new x2, and new x3 is computed before going to the next iteration. Whereas in Gauss-Seidel, once we have the new x1, we will use it. Once we have the new x1, we will use it, and once we have the so we won't wait until the brand new iteration to use the one. Whenever there's a new information about x1, x2, x3, we will use it on the other equation. It's a little bit more convoluted than Jacobi iterations. The small changes and very intuitive. You can do those examples to see if you get the same results. And there's not much. It's not very systematic, and there's not really much math involved, just intuitive. So that's it for LU decomposition, the larger title, and that is it for lecture 9. Yeah. Okay, so lecture 8 and 9 are similar topics. That's why I assign homework, and you have more questions at the back. You are welcome to try. Then next lecture is a different topic. So this is the end of this solving linear system of equations area. So we will start with the next lecture on Tuesday.